So hello everyone. Uh, so we have some remaining topics that we'll discuss today. Um, so in this syllabus, several things have been left out. So I'll just list them here and then we can discuss them one by one. So in this pipe flows, there is some portion left about pumps as well as some more things about some correction factors. So let me just try it. In pipe flows, we need to discuss a bit more. Then there are flow meters. We have already discussed pitot tubes, venturi meter also to some extent. There are orifice meters, rotameter, and some non-invasive flow measurement techniques like magnetic flow measurement and so on. Or just by looking at the flow, you can tell something about the flow. That is also there. Then flow past, so I'll just write flow meters. These are the topics we have partially discussed. Then there is flow past immersed bodies. We have discussed Bernoulli equation, flow past airfoil. We have already discussed flow past a sphere. Okay. We have not discussed creeping flow past a sphere. So flow past immersed bodies. So creeping flow. We just discussed the creeping flow equations, but we did not apply them to any particular flow situation. So creeping flow past a sphere has not been discussed. Then there is introduction to boundary layer theory. What is a boundary layer? Okay. Then one more topic within boundary layer is Karman's momentum integral theory. Okay, that we need to discuss. That comes under boundary layer. Then there are drag forces on a flat plate and on other bodies such as sphere, cylinder, and so on. So drag on various objects. Drag on flat plate and other objects. And there is coefficient of drag, CD, you can call it. And CD depends on Reynolds number. So CD versus RE plots for various objects. Okay. So this is flow past immersed bodies. And then we have some industrial equipment such as pumps, impeller. Impeller is a part of a pump. Then blowers, fans, compressors, and so on. That comes under flow machinery. And here what we do is we apply this theory that we have discussed till now on these things. So we'll discuss some of it today also. Flow machinery, pumps, fans, blowers, and so on. Okay. Then within pumps, there is a topic about performance. Efficiency. Then comes a part where we discuss about cavitation. Cavitation phenomenon we have already discussed. in brief. So cavitation causes some problems within a pump because in a pump there are blades that are rotating if it is a centrifugal pump. And we discussed that if there is a fast moving object, then it creates some um, low pressure zones within the fluid, and that can cause the fluid to locally evaporate or boil. It is similar to boiling. So that causes a reduction in the performance of the pump. Okay. So there is a related topic called NPSH, net positive suction head, which is related to cavitation. That has to be kept in mind while placing a pump or designing a pump. Okay. Then there is a topic on priming of pumps. Okay. And this is about flow machinery. Then there is a topic on separation. Separation of particles from fluids. All right. So there is centrifuge. If you have heard about centrifuges that are used in biology labs or chemistry labs, so you have centrifuge, which is an equipment. It separates solid particles out of fluid in which they are mixed. So there are different kinds of separation processes. We will discuss mainly these two equipment which are used for separation: centrifuge and cyclone. Cyclone separators, centrifuge separators. There is something called gravity settling also, which is the most simple way of separating solids. You just leave a fluid in which some solid particles are mixed under gravity in a container, and the solid particles will settle down. If they are heavier than the liquid, if they are denser than the liquid, otherwise they will float. Okay, so that is known as gravity settling. And there you can find out the time which is required for separation of the particles based on this theory, where we will discuss creeping flow past a sphere. So you can imagine that there are several particles, and we can assume that they are roughly spherical. If there is some other size, we can find out a solution for creeping flow past that shape, cylinder or cone or cuboid. Okay, if there are several spheres, let's say, which are very small, and because they fall very slowly, you can find out the Reynolds number for them, rho Vd by mu. Rho will be the density of the fluid, V is the velocity with which the particle is moving in the fluid. So if these are very small particles, you can imagine that they will fall very slowly inside any liquid. Even very small particles in air fall very slowly. Dust particles, for example. And d is the diameter of the particle, mu is the viscosity of the fluid. So you can see that Reynolds number is very, very low here, less than 1, much less than 1. So there you can apply this assumption of creeping flow. We derived creeping flow equations, which are derived from Navier-Stokes equations after these assumptions. Okay, that Reynolds number is very, very less, close to 0. So here from this you can find out the settling time for a size distribution of particles. Okay, that is gravity settling, and then there are centrifuge and cyclone, which we'll discuss. And then another topic, a small topic, is size reduction of solids. So why is this being discussed here in fluid mechanics course? When there is mining, uh, coal mining or any other kind of mining for metals, for example. So you have very big chunks of solids, and then you have to reduce the size of those solids and then filter out the material. If in case of metals, it is metal or coal, you have to separate them from the dirt, the mud, or other foreign substances. So first you need to reduce the size from the mines, whatever you get, reduce the size, and then reduce the size further from coarse to medium to fine, and then you use any of these processes of separation to separate out the required uh, material, metal, coal, or whatever is important in that mining. Okay, so what is the mechanism of this size reduction? How much energy is required to reduce the size of the solids? How much energy is required, and what kind of processes are required from going to very coarse chunks to medium, and from medium to fine particles. Okay, so as you'll see, this process doesn't require that much energy as this process. This requires about 90% of the energy in the entire process. Okay, we'll discuss that a little bit. Okay, so these are the topics that are left. So what I'm thinking of doing is I'll send some reading material for some of these topics, and some of the topics we'll discuss here. So first, in order to maintain the continuity from the last topics that we discussed, we'll discuss pipe flows, whatever is left of the pipe flows here. So we'll discuss Bernoulli equation, which I can write here again. So this is a constant for a streamline, and given that all the assumptions are correct, it is frictionless flow and so on. But for a pipe, you will always have some friction, first of all. And the other thing for a pipe flow is that at any cross section, the velocity is not uniform. The velocity changes from wall to the center line. Okay, it is not uniform. So this is not correct. What it actually looks like is this for a laminar flow, and for a turbulent flow, it is more or less uniform. At the walls, it has to go to 0, but for a turbulent flow, most of the cross section has uniform velocity, quasi steady uniform velocity. So for turbulent flows, it is very easy to apply this equation, because if you want to apply this equation at two cross sections of a pipe, let's say cross section number 1 and cross section number 2, then the kinetic energy, because this is an energy conservation equation, we are saying that the energy because of pressure, the energy because of the kinetic, the movement of the fluid, the kinetic energy, and the potential energy, that remains conserved from the first section to the second. So if the velocity is same at all the points in a cross section, then we can take any velocity here This is V, and pressure we are assuming is same at the cross section, at the entire cross section, and we are assuming that the pipe is so thin that uh, within a cross section the height differences don't matter. Okay, so the only height differences that matter are these two. Okay. This difference in height. If it is an inclined pipe and this is z equal to 0, this is z equal to 0. That's it. Okay. But for a laminar flow, because it is known that the velocity profile is not uniform, velocity is not uniform, it is paraboloid. So what velocity do you take here? Okay, either what you can do is, if you know some streamline here, let's say at the center line, then you can take the center line velocity only and for that center line. But in general, for practical flows, the center line velocity is not generally known. What you know is the average velocity. How do we know the average velocity? It is very easy to know that. You put a bucket at the end of a pipe and you measure the flow rate. So you notice in how much time does it fill 1 liter or 1 meter cube of this bucket. Okay, then you will get to know the flow rate. Class. Okay. Okay. Yeah. So from here you get the average velocity, V bar. Now, if you want to write this equation in terms of V bar, the average velocity, P by rho g plus the average velocity plus Z equal to constant. This is not true anymore. Okay. Because this equation was valid only for a particular streamline, not for the entire cross section. We cannot just equate V and V bar. V is changing throughout the cross section. So how do we handle this? We go back to the energy equation, the actual energy equation, which comes from the first law of thermodynamics. Okay, and integrate that at the entire cross section. So the reading material is there. I'll send you. The derivation is there in the book, Fox. There, what you get is actually an integral over the entire cross section. When you integrate the energy equation at the entire cross section, V square by 2, which is the kinetic energy, and rho V, which gives you the mass flow rate. And this, if you want to equate with something that is in terms of the average velocity, V bar square and rho V dA at the entire cross section A, and you put some constant here, alpha, for a particular kind of pipe, then because you know what is the form of this velocity, we have already derived the velocity profile. You can substitute it here in place of V, and what you will get is, for the laminar flow and for a circular pipe, alpha is equal to 2. So here you have alpha, which should be multiplied here, and alpha is 2 for a circular cross section pipe and for laminar flow. For turbulent flow, alpha is very close to 1. So for turbulent flow, you don't have to put any alpha here, it is 1. And you can take the average velocity. Okay. So now the equation becomes P1 by rho g plus alpha 1 V1 square by 2g plus Z1 P2 by rho g alpha 2 V2 square by 2g plus Z2 and any other frictional losses that occur in between, that will be in the HF term. So this is the equation for a pipe where V1 and V2, these are average velocities. Okay, is there any question? Okay, I hope this is clear. Now we'll discuss a bit about pumps. What do pumps do in a flow? They actually increase the head. They give some energy to the flow, right? That's what pumps do. And what is pipe doing here? It is actually taking energy away, which is shown by this term HF. So some energy is lost by this because of the pipe frictional losses. And if you want to add some energy here because of the pump, you have to write minus, and then you can write H pump. Okay, where H pump is a positive quantity, or in other words, you are adding H pump to the left hand side. Okay, and which are the 2 points where we are writing this 1 and 2? Where are they? This is point number 1, this is point number 2, and this is the pump. Okay, so pump is doing some work on the fluid. It is adding some energy to the fluid. So you have to subtract this H pump from the second side or add it to the first side. That gives you a modified Bernoulli equation for a pipe with a pump attached to it. Okay. Now if you notice the dimension of each term here, it is meters in SI units. Because of this Z1, you can directly say that it is in meters. In other words, this is also work per unit weight. Okay, that you can see work has dimensions of so I am writing the SI units here. This is mass times acceleration times a displacement, because that is force times displacement, that is the work, and then weight is mass times gravitational acceleration, that is meter per second square. So you get meter. Okay, so each term is work per unit weight. If you want work per unit mass, then you can just multiply with gravity everywhere. You will get work per unit mass. So if you want to find out work done by pump, that is mass flow rate times H pump, head raised by the pump. Okay, this H pump that we have written here, that will be the work done. So here work done per unit time, and this is mass flow per unit time. All right. Okay. And you can write this as m dot. Okay, sorry, there has to be a gravity term also, because we have weight here, that will be mg. So I have to write in terms of pressure, velocity, and z. then it is E by rho plus alpha v square by 2 plus gz after multiplying by gravity everywhere, gravitational acceleration at point 2 minus at 1. Okay, so this is work done by the pump, and you can find the efficiency of the pump. Is there any question? Okay, all right. So this is the work done by the pump given to the fluid, and W dot in is the work done on the pump or the energy given to the pump. Okay, in terms of electrical energy or the energy given to the blades after all the electrical losses are subtracted. So it depends which efficiency we are talking about here. Okay. So there are special names given to these points 1 and 2. This point 1, which is before the pump, this is known as the suction side of the pump, from where the pump sucks the fluid in. And the point 2 is known as the discharge side of the pump. So the side to which the pump discharges the fluid. Okay. I hope this is clear. Now we'll go back to the list again. Okay. So these flow meters, that means how do we measure the quantities related to a fluid flow? For example, velocity, pressure, mass flow rate, volume flow rate, which can be found from velocity again. Okay. So mainly velocity and pressure need to be found. Pressure sensors are there. So they can be in the form of piezoelectric sensors. So the devices which generate some electrical pulse on the application of some pressure on them. So those are there. Those are there for solids as well. Okay. If a solid applies pressure on a piezoelectric sensor, then it will give some electrical pulse, and you can measure the pressure. Same principle can be applied for fluid also. So that way you can measure pressures. Now most of the sensors now that you need are for measuring velocity. So for velocity we discussed pitot tube to measure external velocities. So if there is a device, for example a flying plane, on top of that plane you can have a pitot tube. Okay, so for external velocities you can use pitot tube. Even if a pipe is very thick with a very big diameter, you can have a pitot tube inside that also and measure the velocity of the fluid. Okay, then you have venturi meters or venturi tube. So here what you need to do is, let's say you have a pipe, you insert a venturi tube like this in between the pipe. This was the original pipe, and we have put this venturi in the middle. and then you can measure the pressure difference between these two columns here that I have drawn. Okay, and because we know this diameter ratio of the thin section and the thick section, we can measure the velocity in the pipe. Okay, so based on the Bernoulli equation, we know that when the cross sectional area reduces, velocity increases. That is from the continuity equation. And when the velocity increases, the pressure reduces from the Bernoulli equation. So here you will have a low pressure, so the fluid will rise less here, and here there will be a high pressure region, so the fluid will rise more. So this is just an example setup. You can have a different device for measuring pressure differences between the thin section and the thick section, between the section 1 and 2. Okay, so by this pressure difference you can find out the velocity v. Okay, this we have discussed in first few classes when we started with the fluid dynamics part after the statics part. Okay, then a similar device is orifice meter, where instead of having a shape like this, what we do is we have a plate in the middle and there is a hole in that plate or orifice in that plate. Okay, so now if you see the flow streamlines, they will look something like this. Okay, and it looks like a Venturi meter again. Here also the streamlines will be like that. And for an orifice meter also you have a similar flow pattern. There are some differences, of course, but this is much easier to make. You don't have to make a shape like a Venturi meter. You don't have to make it so big. Okay, you can just have a small piece of equipment which is very easy to construct. You just have to put a plate with a hole in between two pipes. Okay, that is orifice meter. And again here you can measure the pressure difference between this point and this point. Okay, 1 and 2, the thin section and the thick section. Okay, now to measure the velocity, to measure the flow rate, there is a device known as a rotameter. What we have here is, let's say there is a pipe and there is a bend like this. For this to work, we need to have the section vertical, okay, in the direction of gravity. Then you have a conical section here. And there is a solid. Okay. If there is no flow, this solid will come down and plug this entire thing so that there is no flow from here. There is no gap in the pipe for the flow to occur. When there is some flow, this solid goes up, okay? And when the flow is steady, this solid will remain there at some height, and there will be flow from the sides, from the periphery, this annular region, okay? So as the solid goes up more and more, there will be more space for the flow to happen. So the flow rate will increase as the solid goes up. And from this, what we can do is we can balance, we can do a force balance on this solid. We know mg, and there will be some drag relationship, okay? This force of drag. So Fd is equal to mg, and Fd will be in terms of velocity of the fluid that is flowing past this solid. That's why we have to study this flow past different bodies, and we have empirical relationships for different solids. So this is in terms of velocity of the fluid. So from here we get to know the velocity of the fluid, and there are readings here from which you can find out how much is the flow rate or velocity of the fluid that is flowing. Okay, so this is the principle of rotameter. And then generally for air, this another equipment is used, which is known as hot wire anemometer. So what you have there is this is an electrical equipment. You have two arms here, and there is a wire held in between these two arms. Let me draw it in a different color. This is the wire. Okay. And because of the flow of electricity and because it has very high resistance, this becomes heated up. And when there is some air flow past this equipment, some heat is carried away by the air, so it cools down. And how much it cools down depends on the velocity of air. If the air is flowing slowly, then it will not cool it that fast. Okay. And the resistance depends on the temperature of this wire. So there is a graph. This is calibrated. Resistance versus temperature of the wire. Okay. There is some graph for this. All right. So from the voltage drop that is calculated here in the equipment, you can notice the reading there. You can notice the current reading or voltage reading there. It depends on the kind of equipment. So from there you can find out what is the temperature depending on the resistance, and then from there you can know the velocity. So all of this has to be pre-calibrated, and then you can find out the velocity of air or the flow rate of air passing through this equipment. Okay. Is there any question? So these are different flow meters, and there are many more. There is something called PIV, particle image velocimetry. This gives you a detailed view of the entire flow field, not just the velocity at a particular point, in a pipe or in an external flow, but the entire picture of the flow. So from particle image velocimetry, you will get an image something like, so let's say there is a flow inside a box. You will get the velocity vectors at each and every point with some resolution, of course. So here you take pictures of particles, you release some particles in the flow and take pictures at 2 successive time steps. And then using some algorithm, you find out the velocity. Okay. Because now you know how the particle moved from one point to the other point. So it gives you the velocity. And that way you can picture the entire flow field without having to put any equipment in the flow field. So these are known as non-intrusive uh, ways of measuring the flow. Now this flow past immersed bodies, I'll send you a derivation and send you some reading material for these things. Similar for flow machinery also, because we don't have much time today left. I can show you some flow separation equipment today. Let me. Okay. So you can see here, this is known as a cyclone. Let me go to the first slide and yeah. This equipment is known as a cyclone. This is a 3-dimensional equipment. This is a cone here, conical section, as you can see written here. Now you have some dirty fluid here from the left end. This is the inlet pipe. Dirty means it is mixed with some particulate matter which you want to separate. Okay. And this is off-centered. If you see the top view of this will be slightly off-centered, so that when it enters this section, it rotates like this. And because of its weight, it goes down. Okay. The red thing that is shown here, the red line, that is the trajectory of particles, because they are heavier than the gas or heavier than the fluid in which they go down like this. And this thing that is shown here, tails, this is from where you get the particulate matter. And this blue path that you see here, that is the path of the air and the very fine particles which are not separated. So because these particles go down and they carry some fluid with them, because of the no slip boundary condition on the fluid, on the solid particles, because of the continuity equation, something has to go up also. Okay, only then continuity will be satisfied. So these particles go down and they send up the fine particles plus air. So from the top you get the clean air, and at the bottom you get these tails or the solid particles. So if I show you some industrial hydrocyclones or cyclones, they look like this and they work in parallel. So you have several cyclones working in parallel. You can see here. So this top part, if you see in the first image, the left top image, the top part that is coming out of this cyclone, that gives you the clean air. Okay, and this pipe that you are seeing here, if you can see the hand tool here, okay, so that pipe is the inlet for the cyclone. So that is off centered at one end of this circular top cross section. Okay, this is not directing the flow at a diameter of this circular cross section. This is slightly off centered, so that there is a rotating motion of the particles as well as fluid. Okay, and why do they have these parallel cyclones? Why not have a single big cyclone? So that is related to the efficiency of the cyclones, which is given by this equation here. So this is known as separation factor, which is the centrifugal force to the gravitational force. Gravitational force is responsible for pulling down the particles, the heavy particles, and centrifugal force separates the particle from the fluid. Is it clear? If there is any question, you can ask now. Okay.
So, please repeat this point.
Okay. So this separation factor is Fc by Fg. Fc is the centrifugal force and Fg is the gravitational force. So what centrifugal force does is it sends the particle away from the center of the tube. Okay, because the heavy particles will tend to go outwards. Uh, is that something that is known to you?
Yes, sir.
Yeah. Okay. So if you have a mixture, then heavier particles tend to go outwards if there is a centrifugal field. Okay, if there is a rotational motion. So that is what separates the particles, and gravity is what pulls them down. Okay, if there is more gravitational force, then they will tend to come down quickly. Okay, let's say there is less centrifugal force and more gravitational force, then it will pull down fluid and particles without them being separated. Okay, so they won't have much time to separate, but it will pull down quickly. So we want less gravity and more centrifugal force. That increases the separation. It gets more time to get separate. Yeah.
Yes, sir.
So that comes out to u square by rg. U square is the tangential velocity squared by rg. So radius of cyclone, as you can see, is in the denominator. So if it is a smaller radius cyclone, then it is better. Okay, so you don't want to have a big cyclone. You can have several small cyclones working in parallel. So that increases the efficiency or separation factor of a cyclone. So I'll send all this reading material to you as well, so that you can read, and in the next class we can just discuss what you have read. Okay, thank you. So we'll end here.